All right, so today we are going to be starting to delve more into non-parametric methods, so sort of moving beyond linearity. And as kind of a theme in what we've been moving towards, so as we move away from linear models, we tend to lose out in interpretability for inference, but we gain predictive power. And flexibility for fitting models. And so to kind of, it reiterates in a lot of the like linear models, it's very easy to interpret like beta coefficients and what that means for its relation to the outcome. But as you have things that start to become more non-linear and where you are using sort of more non-parametric methods, that kind of straightforward interpretation begins to decrease a lot more. But we will sort of talk about some hybrid methods either today or in the next lecture about how you can get kind of a mix of both of those things. Okay. So we are going to go through a whole series of increasing complexity in a family of regressions that increasingly provide for flexibility to fit to non-linear models. And so this is kind of the order we're going to be talking about this. So polynomial regression. Then we'll be talking about step functions, regression splines, smoothing splines, and then either today or next class, we'll talk about local regressions and then general additive models. And so the progression from sort of here to here is pretty straightforward. And then 5 and 6 are going to usually be a sort of slightly different approach to regression modeling. Both 1 and 2 will have these things known as basis functions. And so this is either so it's a family of functions or transformations that can be applied to a variable. And so we'll talk about what that sort of means. But we actually have already, in a previous lecture, talked a little bit about polynomial regression. And so here we'll start to think about it a little bit more formally, but more so in the context of starting to move away from your regular sort of linear model and think about what that means and how that can sort of progress to some of these other nonlinear models, such as the splines. All right. So as a quick refresher, the polynomial regression is a transformation of our linear model, which might look something like this: beta 1 xi plus ei into something that might look more like this. So beta 0 plus beta 1 xi plus beta 2 xi squared plus beta 3 xi cubed, and so on and so forth, until you have however many polynomials. Okay, and so if you recall from our previous lecture, there was this example where we would have some points, and then you could fit some kind of nonlinear curve to it by including polynomial terms of your x. And from a practical perspective, doing this kind of transformation, so this can become overly flexible and take on strange shapes near boundaries of x. So we'll show an example of this in just a moment. And then it comes to this typical question that we've been talking about. If you think about adding more polynomial terms as increasing the flexibility of your model fit, to what extent do you actually start to do things like overfitting? And so that begs the question, how many polynomial terms should I add when I'm fitting to my regression? And hopefully you guys can imagine that the way that we would choose the number of polynomials is similar to the way that we calibrate most of our other models to kind of best allow for the best ability of the model to predict outcomes, which is using out-of-sample validation. And so doing a cross-validation procedure across different numbers of polynomials is going to let you get the best predictive outcomes. So let's go ahead and jump on over to RStudio. And we'll be jumping back and forth a bit more today. So we are going to look at an example that will be sort of being consistently applied as we move through our different nonlinear models. And so let's just go ahead. I'll just go ahead and do this, and then we can see what that looks like. Okay, so you may recall a procedure that we've done like this similar in the past, but now we're going to create a nonlinear version of what we used to have. And I'll graph this in just a second so we can see plus random error. So, before I think we used to do 0.5x plus random error, but now we're actually having the sine cosine business. So this is like extremely nonlinear. And we can take a look at this plot. Y. Okay, so we can see this sort of pattern. You have a lot of points, and in general, it's going to be sort of extremely nonlinear. We can see this pattern here. If I were to fit a linear model, something like this, we could take this plot and add a line to it. And I'll go ahead and run this. And it is kind of what you'd expect, right? You have a line that's going through most of the points, but we might argue that this is not a sort of good representation or a good fit of the actual data. And one way we can look at that is by plotting the residuals. So our x would be our predicted values, and then our y would be the residuals of those values. And if I were to plot this, remember, the thing that we would want to see in our residual plot is a sort of random scattering of points. And what you can see from this model is that this is like very clearly not randomly distributed. And so we could argue that there is like some kind of systematic bias happening. And so the linear model is not going to be a good representation of the true functional relationship between my x's and my y's. And so let's try a polynomial model. And there's a nice little shortcut to this compared to what I showed before, where you can use this function argument called poly. Okay, let's see. Is my screen not updating?
It looks frozen to me.
Yeah, okay. Give me 1 second. Let's refresh the share. All right, in the meantime, while we're waiting, does anyone have any questions so far? No questions, so we can just wait for this to load. We'll have our break super early today. Not sure why this always happens.
Hi, Ellen, I have a quick question.
Yep.
Could you give us some examples of where we might find data like this that's sinusoidal?
That's sinusoidal. I have no idea, but I can definitely point to lots of examples of things that wouldn't be linear. So I don't know, like one thing that might immediately jump to my head would be like daily cases of coronavirus, just as one example. So if you like try to fit a linear model to it, you know, sometimes you can get away with things like exponential growth being transformed into a linear function when you do a log transformation. So things that like curve upwards. But if you look at like a coronavirus daily cases, you often have like ups and downs for like the different waves. Like that would be a pretty easy example of something that would be like a lot of people attempt to run like a linear regression against something like that, which you can do. You can futz around with like transforming things, but at the end of the day, like my philosophy about these sort of things is like if you look at the data and it doesn't look linear, and it's like not linear in the parameters, like why are you trying to fit a linear regression to it? So in this particular example that I'm showing, it's kind of like an extreme case of like what you could do, and we could see like how well some of these approaches fit to this like very nonlinear thing. But in general, if anytime you're starting to run into data sets that contain variables that are like not linear in their relationships, I don't always think it's a great idea to just start running these like linear regressions.
I have kind of a follow-up question.
Mm-hmm.
So I was looking at LexisNexis has like a database where they keep track of
Articles, right?
articles, yeah, with some keyword in it. And I, for a while, was looking at data for the number of media mentions for COVID.
Mm-hmm.
And kind of like what you were describing with like the COVID cases, it definitely had kind of like a pretty massive curve, and it was increasing very substantially with each day. But what was interesting is that you could see kind of a drop on each weekend. So I was curious, like when you have data like that, that's nonlinear in kind of two different ways, if that makes sense. How would you handle that, since it doesn't seem like you could make just one adjustment? Maybe that's something that we'll go over, but that seemed like a good example from what you were talking about that made me curious.
Yeah, so that's actually a pretty good example of what I would think you could characterize using like general additive models, which is something that would go in between like your purely sort of nonlinear versus linear models, because people can think of, you know, some of those differences as being like linearly different, like weekday versus weekend. And in those general additive models, you can apply splines to specific variables. And so we'll talk about what that is, but the general idea is that, like, if you think some things are linear in parameters and some things aren't, you can actually go in and choose which variables you want to make linear versus not. Yeah, and so we'll talk about how that works in a bit. So okay, so we're moving on from our linear model and we're applying this polynomial model. So this, instead of just running y on x, it's going to do the polynomial combinations of x, x squared, x cubed, all the way to x to the 25th power, which I just specify here using this poly function. So you can run this, and if I look at the summary of the polynomial model, you know, it's got a coefficient corresponding to each of the powers for x. Okay, and I can go ahead and generate a set of predictions over the range of the x to elicit a fit of that particular model, so we can plot that. So I'm going to plot, copy this over. So I'm going to plot that the points that I had before along with the linear fit, but this time I'm also going to add the fit from that model. One, y equals polynomial predict 5, and then we'll make the color slightly different. Okay, and so I'll just run this really quick. So remember, with just the line, you've got the red line going straight through all of those points. And now if we run a linear regression with all the polynomial terms, it'll look something like this. Okay, and so you can actually see the blue line doing a fairly decent job, I think, of fitting the points, right? And so already we can see this pretty nice improvement over the red line, and you could argue that this blue line is definitely a lot closer. Now, if we pay sort of close attention to this, I did mention, right, one of the drawbacks is that you can take on some strange shapes near the boundaries, and that is an artifact of like how polynomials work, right? So as you go out to sort of the infinity bounds, you have to go up to infinity or down to negative infinity. So you start getting these weird squiggly things that are happening at the boundaries. And also, I think this middle section probably isn't super accurate, but overall, you know, we might say that this is a fairly decent representation of the function. If I look at the residuals, yeah, so this is definitely way better than the residuals for the linear model. But again, so if our zero line is over here, it looks like there's some kind of, there might be something happening over here where it might be biased upwards a little bit, maybe. And then in the middle, this doesn't seem to be quite randomly distributed. So actually the residuals are following at least my kind of suspicions in looking at the fit of areas that might be slightly suspicious. Okay. So that is application of this one sort of particular model, and how it fits to this data. So now let's go ahead and talk about a slightly different approach. Okay. So the next item on our list is to talk about segmented, also known as piecewise regression. Okay. So our starting point again is our linear regression. But now we can break it up into two components. And more generically into any sort of number of segments. Okay, I see a question from Aditya. Can we use polynomial regression for models where we want to correct for a seasonality? Yeah, so generally, like you could use the polynomial model for any sort of thing. Like for time series, well, I guess it might be slightly different in that if it's something that you know about, you can explicitly add in the variable. So so seasonality, like if you were to add in seasons or months, that might sort of correct for it already. And then if you wanted to do some time-based polynomial term, you could add that in, and that could in itself correct for differences in like seasons. But if you already know what it is, you might as well sort of add in that data into your model.
Right. So for example, vehicle sales, where I know where one can establish seasonality to a large extent, can we use this to avoid getting into the complexity of a time series ecosystem?
Yeah, you could if you just wanted to control for it. Although one of the things is that like a time series based like polynomial variable could start to grab a lot of things, other things that you might want to think about controlling for. So, which is totally fine if you're doing prediction. You don't care. You just want to get the best predictions possible. But if you're still in the if you're still in the inference territory, then it still might be better to get more specific. And the other thing that I'll say is you wouldn't, like, people don't use polynomial regression really because of what I will be sort of continuing to introduce. So as we, it makes much more sense that if you're going to move that direction, you might as well use splines, which I'm kind of building up to, because we have to talk about polynomials, then the segmented, and then that helps us establish the sort of foundation for what a spline is. So if you were to take this kind of approach, you would do some kind of like smoothing spline, to do that kind of application. And I think actually once we get to the general additive models, which is the hybrid version of the linear parameters and the spline parameters, and smoothing the parameters into splines, I think that you'll have I think you'll have a clear sense of how you might tackle that issue.
Thank you.
Mm-hmm.
Alan, could you please explain again what you mean by xi less than beta?
Yeah. Sorry,
Okay,
this
yeah.
is a breakpoint. So BP stands for breakpoint. So basically, let's say X and Y, let's say we have some set of data points that look like this, and then we have some set of data points that look like this. If you fit a regular linear regression, it might look like that. But what the segmented piecewise regression does is it says, okay, let's create a breakpoint somewhere. So this is my breakpoint. And I'm going to run a regression, one linear regression like that, and then one linear regression like that. Okay, that went too far because it went beyond the breakpoint. So let me draw it better like that. Hopefully this is, it is really quite straightforward. You're just dividing the data up and then applying a linear regression to sections of the data. Of course, you can choose you can choose an arbitrary number of breakpoints. You can also choose the location of the breakpoints. So in doing that, this procedure actually becomes complicated. Even when we're thinking about, like, if the more breakpoints I add, the more flexibility it is. And it's the same question of, the more breakpoints, then at what point do I start getting into overfitting? Well, you can do cross-validation to figure that out, but you have an extra dimension of difficulty in that you also have to choose the location of the breakpoints. Okay. So let's quickly jump back into RStudio and take a look. So I'm going to use a package called Segmented, which allows me to do piecewise regressions. Okay, and we're going to do a piecewise.model. And all you need to do is put in the linear model that you've specified. So we'll just put linear model. So this is the LM for the thing that we've already run of Y on X. And then what variable I'm going to segment on. So in this case, it's just going to be X. And then psi is a list of the breakpoints. So I'm going to just simplify this, and I'm going to create some even breakpoints at intervals of every 0.25. So 0.5 to equals 4.5, phi equals 0.25. So this is my piecewise model. Uh-oh, hang on. Linear, seg.z, psi equals list. Oh, I need to put,
Alan, my R says there's no package called segmented.
yeah, it's not a built-in package. So if you don't have it, you'll need to do this, install packages segmented, and hit enter, and then it will prompt you to install
Okay.
the package. Yeah.
Thank you.
Yep. So psi list X equals sequence. Yeah, that's why. So it's going to run that. And then we're just going to do the same thing where we do a prediction across a new set of data over my range of X's. Oh, piecewise dot model. Okay. And let's copy and paste our previous plotting. And let's do a comparison of the we'll do a comparison of the piecewise to the polynomial. So y equals piecewise dot predict, and we'll make this guy forest green. Okay, so let me run this and see what happens. Actually, let me comment out the blue one for a second. So we just see the green. Okay, so you're going to get a similar type of thing here. It's not as smooth as the polynomial curve as you might expect, because you've just got these sort of lines. But I might actually argue that in the end section and in the middle section, it actually is doing a better job. And in fact, we would kind of expect in the middle, like a sine cosine thing to look more like this than what the blue line was doing. And so I'll put the blue line in right now just so that we can see this type of thing. We should expect a like a sinusoidal type of wave to be occurring over the same frequency. And so you see that in the green, but not in the blue, right? This length here is like wider than most of the other ones. So, okay. Let's actually, why don't we look at the residuals as well, just to see what this looks like.
Alan, could you also just walk us through line 25 again? Sorry.
Yeah.
Just what does the seg z thing do? Does that mean that every time x changes direction, there's a breakpoint?
Yeah, so you're actually specifying which variable in the model that you want to do breakpoints for. And then the actual breakpoints are going to be based off of this input in the function psi, and you do a list, because you could actually do breakpoints if you have a multi-dimensional problem. If you have x1 and x2, you could do breakpoints on multiple parameters. So you have a list, and then x, corresponding to the segment thing, is going to sequence each of these big breakpoints. So the sequence, so this function, if you're not familiar, just creates a vector. So I'm going to go from 0.5 to 4.5 in increments of 0.25. So it just creates this vector 0.5, 0.75, 1, and so on. And so the breakpoints that are getting defined by this model are at each of these points.
Thank you.
Yep. So let's take a look. Oh, okay. So I can't actually look at the residuals, unfortunately, because oh wait, no, sorry, my bad. It should be piecewise model, not piecewise predict. Okay, I think it should work. Okay, there we go. Good. So this is the plot of the residuals. Still maybe slightly problematic, but generally I think it looks pretty good. I think at all the kinks of my segments, I think you start to see some weird stuff happening with like a higher density of points, and the residuals increase, which kind of makes sense. And then they kind of contract at in between. So still, I think that this, generally would be a pretty good model. And in fact, I might even prefer the piecewise to the polynomial. If I really had to choose. But generally, right, we can see that both of these guys are are doing a fairly good job, but that there are definite kind of distinct disadvantages or downsides that are happening with respect to both of those. All right. Okay. Any other questions about this?
So would there ever be a time, I actually thought of this because my drawing was sloppier than yours when we were doing notes on the whiteboard, but in my plot, the way that the lines would best fit the data don't meet each other at the points.
Yes.
Would there
yes.
ever be a situation like that?
All the time. Yeah, that is actually, I'm going to talk about that right now. Yeah, you can definitely have instances where they don't meet it. It just so happens that because we're doing like really continuous stuff here, that they tend to meet. But definitely that is a big issue. And that's actually a particular issue for this next example that we're gonna talk about. But yeah, you can have discontinuities for sure. Okay. So maybe some of you guys are already starting to think of this, but it's black. Let's talk about splines. And yeah, I'm not sure how many of you guys have actually heard of these, but this is the natural extension to improving the models that we've just talked about. And so what a spline is a combination of the two. It is a piecewise polynomial function. But it's a little bit more than that. There's the thing that makes it a spline has to do with this problem that that Sarah just posed. So some hidden details. Now, because you are able to sort of combine the flexibility of doing a piecewise with the flexibility of the polynomial, you actually have more than enough flexibility to capture basically any kind of shape without getting too crazy on the polynomial end. And so the vast majority of spline applications in reality don't use polynomials beyond cubic. So once you have x cubed, it's the combination of the flexibility from an x cubed function with the piecewise, you typically don't see too many examples of splines using more than this cubic polynomial function. So the first kind of cut is a piecewise cubic. So this is 2 cubic, so polynomial regression lines, regression line segments. Okay, and so I will attempt to draw something like this, and maybe something like this. So if this is our breakpoint, you may get something that looks like that, along with something that looks like that. So this is the problem that Sarah was talking about, in that your segments don't actually line up. So we can improve this, right? We can go to create a continuous piecewise cubic function. Okay, and so this is the same thing plus additional constraints that lines touch. Okay, so if I were to draw kind of the same thing, my breakpoints are like this. In this case, you might have a fit that goes like this, and then like that. And actually, let me try and make this a little more extreme. It might look like that, and then like that. Okay, and so we can further improve this. And so this is going to be what our ultimate cubic spline is. This is plus the additional constraints that lines must be smooth. And so this means first/second derivatives are continuous at cutoff. Okay, so finally, your line might look something like this. So now you notice that it's much smoother here. And as a point of nomenclature, the breakpoint for a spline is known as a knot. And the nomenclature is different to indicate the fact that the continuity for the line must be smooth. So when we say breakpoint versus a knot, there is actually a sort of technical difference between the two. Okay. So the transformation of our yi is equal to beta 0 plus beta 1x is slightly more complex. So we have something like this. And so there's actually what's known as this basis function that is a transformation of my x's. That is some kind of cubic function, right? And each of the different splines that we'll talk about have slightly different basis functions. And that's not a detail that you sort of need to memorize, the basis functions. So as I was mentioning before, cubic splines are the most common. And we trade off the polynomial. So having lots of x to the k terms for knots. Okay. I'm going to go a little bit longer before we have our break. So knots provide flexibility. So if we have something like this, wish I could copy and paste my graphs, but unfortunately not able to. So we're going to draw this a couple times. So you can have 0 knots, you can have 1 knot, you could have 2 knots, and so on and so forth. So, oops, let me use a different color. So you might have a knot here. You might have 2 knots. Maybe it looks like something like this. And your fit would look different depending on how many knots you have. You could have something like that, or something like, okay, I'm just, we'll see examples of this. But essentially, as you add more knots, you're increasing the flexibility of the model to do more like curvy things, right? And same idea for anything that adds flexibility into the model. At what point are you worried about overfitting? Well, we can figure out how many knots that would best do out of sample prediction using cross-validation. So again, coming back to this theme about using out of sample prediction as a way to calibrate this number of knots parameter that allows us to introduce flexibility into the model. Okay, so let's take a quick break here for 5 minutes. Yeah, feel free to ask any questions if you have any. Yeah, while we wait. Okay. Let's continue on. So before we jump over to R to talk to sort of demonstrate application of the spline, one of the things that should be noted is that there are a lot of kind of incremental improvements that have been made on spline fits. So we've been talking mainly about these cubic splines, which are not, I would say, quite as popular anymore because of some of these improvements. So natural splines. So cubic splines can have high variance in outer ranges of predictors. And so natural splines, what they've done is to add constraints. So so that function is linear at boundaries. And this has more to do with kind of the error around the spline. So if I look at an x versus y, let's see, if I have a whole bunch of data points, and then I've got my knots, something like this. You can draw some kind of fit. For a cubic spline, you may find kind of an increasing sort of error at the boundaries. So this would be cubic spline variance. But for a natural spline, it might be kind of similar, but then it would become straight at the boundaries. So there is a improvement in the overall sort of variance. And so natural splines these days, I think, are somewhat preferred to cubic splines. Okay, so let's jump on over to R. And we're going to use another library called Splines. Again, this might be a library. This is not a sort of base library, so it might be something that you'll have to install separately. So you would use install using install packages, Splines. So, and yeah, let's go ahead and do this. Cubic spline 1. And it actually still uses the linear model function because it's still using the linear model, but it's introducing the nonlinearity through your basis functions. So it actually uses this function called BS, standing for basis, which you're going to do to your x. And then it's going to ask for some number of knots. So my knots are going to be, in this case, I'm going to choose them from 0 to 5 in increments of 1. And I want to be able to look at the prediction over a range of values. So I'm going to predict here the cubic dot spline 1 over a set of x's from x equals 0 to 5 in increments of 0.01. And then I can even specify a standard error around the line so we can see what that looks like. Okay, so let me go ahead and run this. Oh, I didn't load the splines library. Okay, that's fine. I'm not choosing my knots very strategically. I'm not doing a very good job. So we're going to add in the prediction as a line to show the fit of the spline model. And y is equal to cubic dot predict 1 dollar fit equals blue. Okay, and actually I'm going to run, so I'm actually going to show you guys what the cubic predict looks like. And this is actually a little bit different. You can see here it's a list of items because it actually contains both the fit itself as well as the standard error of the fit. And so we're going to plot that in here. So instead of just the fit, we're going to do the fit plus 2 times my standard error, which will give me my 95% confidence interval. So we'll leave the colors blue, but we're going to make the line dashed. Okay, and that's the one above the line, and we need one below, so that's minus 2 times the standard error. And I'm going to go ahead and just plot this. Okay, so this is our fit for our cubic spline with a 95% confidence interval of the, of any sort of of the mean value of your prediction. So in this case, we can see how many knots did we have? We had 0 to 5 in increments of 1. So we had a total of 6 knots. So if you have 6 knots in here, it's that original line from your linear regression, and then you start to introduce a little bit of flexibility, as can be seen here. And remember that it's not going to go do all this crazy stuff because of the constraint for doing the smoothing, so that the first and second derivatives at the location of every knot has to be continuous. And so what we can do then is to increase the number of knots. And so I'm just going to go ahead and copy and paste this thing here, but now I'm going to change it. So instead of going in increments of 1, I'm going to go in increments of 0.5. And so we're going to call this spline 2, predict 2, cubic spline 2. And so now we're going to have twice as many knots. And let's see what happens here. And then I can go ahead and copy and paste this guy. And we're just going to use number 2 here, number 2 here. And I'm going to change the color to red. And let's go ahead and add onto this existing plot the new regression model where now I have twice as many knots. Okay, and so here we're starting to see a little bit more curvature. And you remember one of the artifacts we were discussing was that you tend to start having this larger variance things sort of happening along the outsides. And so we can already see that where the sort of size of this is generally larger than in the middle. And then we are starting to see some kind of better fits here. So let's go even more extreme. So let's try in increments of 0.3 instead of 0.5. Do the same thing, run this model, and then I will copy and paste here where I'm using predict 3. And let's do orange instead of red. Okay, awesome. So all of a sudden, we're starting to mirror closer and closer to these points. It's doing a much better job, I would say. And let's try one more time. I'm going to sequence by 0.1. So now, in comparison to the very first model that I ran, we are now looking at a model that has 10 times as many knots. And if I run this and look at that fits, and then we'll change the color as well in 1 second. So let's do forest green. What you can see happening is that now I think arguably I'm doing a really good job at kind of fitting along these points. And so the model itself is essentially the same. You're just adding, you're making the basis function slightly different because you are adding in more and more knots into your model. And so with let's see, how many 6 times, where are we? So a total of 6 times 10. So like with 60 knots, you end up with this green line, which probably out of all the models that we've looked at so far is probably going to be doing the best, especially when it comes to out of sample prediction. Let's try a super extreme case now. And hopefully this works. Doesn't always work for some reason. But I'm going to do 5. And let's go every 0.0025. So now you are adding, what, 4 to 1, 4, something like 4,000 knots. And let's grab this. We're just going to make a new plot here. This is going to be 5. So what happens when we add a crazy number of knots? Oh. You'll notice right now the model is running, and it definitely takes a lot longer to run. Oh, something went wrong here. Singular matrix. Okay, so too many. Let's see. What if I do 0.05? Okay, still works. Okay, you can see that our fit got really crazy here. It's going up and down a lot because you have so many knots that it has flexibility to go wherever it wants and still end up hitting through your points. And actually, if you looked at the mean squared error, this would probably be lower than our previous models because it has the ability to actually move through all of the points. But this is a really, really obvious example, I think, of overfitting. I actually didn't want it to be this extreme. Let me see what happens if I do this. Yeah, okay, so this is better. So you can see like we're adding in more and more flexibility, and what ends up happening is the line starts to it jiggles a lot more, which means it's trying to capture some of the noise. So you decrease the bias, but you're increasing the variance, right? Our same thing about overfitting. And so this is a nice little example of like what happens if I introduce too many knots. And so how do you choose the number of knots? Again, the best way is to do cross-validation. So let's show the example of a natural spline. So it's the same thing, but instead of BS, which is for a generic basis, we're going to use NS, which stands for natural spline, X, with a 10 degrees of freedom. And the nice thing, I think one of the more sort of convenient things about this is that you just tell it how many knots that you want via the degrees of freedom, and then it'll choose the locations for you. You can actually specify the locations explicitly, as you can see in this function. You have this knots parameter, but this and I should probably learn this, but I don't actually know exactly how it chooses the locations, but it'll do it in sort of the best manner possible. Okay, and so we're going to do the same thing, doing this prediction business. And we're going to have the standard errors as well. And then let's just go ahead and grab this, copy and paste the plot. And we just need to change it from a cubic predict to natural predict. Okay, so let's run this. Oh, I did not include the bottom one. So -2. Okay, so similar type of thing with the natural spline. But we can increase the number of knots. So let's do, in this case, well, let's do 15. See what this looks like. And again, I'm kind of guessing and checking here for the number of knots, but the sort of systematic way you would do this would be to use some kind of cross-validation procedure to grab the correct number of knots. Okay, so let's do a comparison. Getting better already. Oh, let me make this a different color. Yeah, okay, so getting better already. And let's just double the number of splines here. We'll do 30. And we can see that it's going to be doing a much better job. And let's change the color. I think we were using orange before. Okay, and so we can see a fairly close fit. And I can actually go ahead, I'll just copy and paste this over. I can compare my cubic spline to my natural spline, and we can see the differences between kind of what we consider are approximately two sort of best models. In this particular case, the difference is going to be very sort of marginal. But what you can see is that the natural spline tends to have slightly better standard errors about its mean, particularly in some of the extreme spots, such as the boundary conditions. So the red is narrower than the blue here, and in the middle part where there appears to be a lot more nonlinearity, it does a slightly better job. And I've actually added in a black line for the true function. So if you remember, we generated these points based off of a true function that we actually know, so we can always compare against that line, and you can see how each of these models do against that. And then just one quick sort of reiteration, right? We can just as easily go too far in the natural spline example. So here I'm going to have 300 knots, and we could just really kind of quickly, easily see that you get this issue of overfitting again. You're fitting to the noise as opposed to the true function. And the way to avoid this, right, and to choose the actual proper number of knots is via some kind of cross-validation procedure. Okay.
Yeah, I have a quick question.
Yes.
Is there any like rule at that limits, like that puts a limit on the maximum number of knots, like based on like the number of data points we have?
Yeah. So you can, in theory, have as many knots as you want. But in reality, you would never really want to have more knots than the number of points that you have, because then you just end up doing this up and down. Like just as a rough example, let me clear this so I can draw. Yeah, okay. Yes. Oh, hang on. Clear everything. Okay, so if I wanted to, I could I could have 3 data points here. And you could introduce a knot at every single point. And actually, it's a good segue because this is what we're going to talk about next. And when you do this, you are guaranteed in your function to like hit every single point. You can go beyond that. I can, in theory, I could add more knots, which would let me go like even crazier. And I would still be able to hit all of my points. So yeah, there's not really a good reason to have that many knots. But in theory, you could. Okay. So let's actually talk about this principle. So the like final level of splines that we're going to be talking about is something known as a smoothing spline. Okay, so in general, we want to minimize the residual sum of squares. And in the case of splines, you have something that looks like this, yi minus g of xi squared, where g xi is the spline cubic function that constrains the first plus second derivatives. To be continuous. Okay, so let's now consider you had a knot for every point. Okay, so this is getting to what Trisha was talking about. What happens if we just add a knot for every point? I might see something like this, right? So kind of repeating what I had before. You might see, okay, we're gonna draw this sort of dotted line to represent the fact that you've got a knot there. So you're putting a knot at every point, which ultimately lets you do something like this. Okay. And in this case, we have perfectly minimized the RSS. But now we have overfitting. Okay. So this, in analogy, is really similar to the ridge regression and the lasso regression that we talked about before for our linear model. Because what those models did was they added flexibility by including all the variables and then adding a penalty term. In this case, we are increasing flexibility by adding a lot of knots. And we can do a very similar type of procedure where we add a penalty term. So the way they do this is shrink the second derivative. So we're going to have our term here, I equals 1 to n of yi minus g of xi squared, which is what we had before about the RSS. But now we're going to add in a lambda, which is a tuning parameter, similar to lambda in our ridge and lasso regression, multiplied against the integral of g prime t squared dt. Oops. And so this is the penalty function. Okay, slightly less straightforward, but let me describe sort of qualitatively what it does. So like a ridge regression, this penalizes the function by encouraging quote unquote smoothness. So the rate of change of the slope should not be big. So in this case, if I have a whole bunch of data points, let's line out a little bit more, and I'll just copy it here. So if I have a low lambda versus a high lambda, what you end up seeing, right, since I have a knot at every point, if my lambda is really low, I could get something like this. But with a high lambda, it might look something like that. And again, this has to do with my penalty term here. And it enforces a penalty that makes it so that if the line that you're fitting through your points changes its slope very rapidly, right, based off of the second derivative, then it will have a larger term in the penalty, which you're trying to decrease. So as your lambda goes up, it's going to make your line smoother and smoother and less prone to having these larger and abrupt changes. And then the question is, well, how do we choose our lambda? And hopefully this is all getting really obvious to everyone. You can choose it by cross-validating against prediction out of sample. All right, so let us go to our final application of splines in R for the day. SP model 1. So this is a smoothing spline. So the way this works is with a function called smooth.spline. X equals X, Y equals Y, S par equals 1. So this is the penalty parameter. And if I run this, we can see what happens. So plot xy, color equals gray. And we're just going to have do lines for this. It makes it a little bit easier compared to some of the other models that we did. So let me go ahead and graph this. Okay. Our penalty parameter for lambda is very large. Okay. We're setting it at this value equal to 1. And because it's really large, it's so large that it's preventing even though you have, okay, how many data points do we have? I think we have 1,000 data points. So there are actually 1,000 knots in here, but this penalty parameter is preventing the line from changing its slope. And therefore it's going to end up looking very much like a straight line. I mean, you can see a little bit of the perturbations, but right, generally it'll look like this. So we can continue to decrease the size of the penalty all the way down to 0, and we can see what happens to the fit as we progressively decrease the size of the penalty. Let me do this one at a time. Okay, so that's our first one. At 0.75, we can see, okay, we are now allowing the line to move a lot more. And you can see this really interesting thing happening, right? So the waviness kind of corresponds to these peaks in your sinusoidal curve. And that's because it's allowing this rapid change to happen because the change in the RSS is balancing out against the penalty term, allowing that slope to change rapidly. Let me change this to forest green. Okay, and so now once we get to a lambda value 0.5, you can see, okay, it's doing a really good job of getting close to these points. And as you even progress further, you start to see, oops, you start to see, particularly in certain spots, like right over here at the edges, right here, and over in this area, there's some squiggly lines happening as it starts to, the flexibility is high enough where it's starting to fit to the noise. And the last one, you have lots of overfitting happening because you have too much flexibility in allowing the knots to change the slope very rapidly. And so you can balance this by figuring out what the right parameter is. So like I said, this harkens back to me giving some of the examples and manually calculating the cross-validation. You know, that is how, because it is so common, the procedure for doing the cross-validation is often built into these functions. And so kind of as a final example to show you guys, my SP model for my smooth spline, instead of specifying the penalty, I can make it do some kind of cross-validation to figure out what the correct penalty value is. And so this model that I run here is definitely going to have the best predictive ability for out of sample prediction compared to anything over here. And we can take a look at what this looks like. So if I were to plot this, And actually, let me go ahead and just grab the actual, so this is the true value. And then let's plot SP model blue. Okay, and so this blue line is the smooth spline prediction, and that's almost entirely over the black line. I guess it messes up a little bit over here, but otherwise you can see the actual black line compared to the predicted blue line is doing a really good job. It's very close to the true sort of function of the fit. Okay, and so there you have a really sort of nice demonstration, right? If we think back to the original linear fit of this line just plowing right through all of these points, we have gone sort of step by step through the evolution of improvements to do nonlinear fits. So this is, some kind of semi-parametric model because you've still got linear in form, but where the parameters themselves go into these weird basis functions or cubic splines with all of these constraints, right? So we don't really get into the mathematics of any of that. But you can see that these splines have become these really powerful tools to do these sort of highly nonlinear fits in your data. And we will sort of continue to talk about some of these other sort of really different procedures, but also, we're gonna move a little bit back towards this struggle between inference and prediction and show the use of these nice hybrid models that employ some of the simplicity of the linear models while incorporating some of the complexity of these spline-based methods. And we'll cover that next class. So this is a good ending point. We'll stop a couple minutes early today. And let's see, logistics. We'll have the project proposals are due on Friday. I owe, again, one or two of you guys emails who sent either yesterday or today. You should expect some response from me pretty soon. Otherwise, yeah, I think everyone's doing a pretty nice job on having ideas for their proposals. Just make sure to get those in by the end of Friday. Homework 3 will be due next Wednesday. And other than that, we'll just end early today, and I'll see everyone next week.